Our sun. It's a mighty ball of fire, a churning furnace of nuclear fusion that bathes our planet in light and warmth. It's the anchor of our solar system, holding everything in its gravitational embrace. But the sun isn't quite the center of our cosmic dance floor. Imagine yourself as an ancient astronomer standing beneath a sky teeming with stars. You have no telescopes, no satellites, only your eyes and your curiosity. From your perspective, it seems as if everything revolves around Earth. The sun rises in the east, sets in the west. The stars wheel across the heavens throughout the night. It's a powerful, intuitive observation, and for centuries it formed the basis of our understanding of the cosmos. This Earth-centered view, known as geocentrism, dominated astronomical thought for over 1,000 years. It's a testament to the power of observation, but also a reminder that our senses can sometimes mislead us. The universe, as we're about to discover, is full of surprises. Our understanding of the solar system's true nature didn't emerge overnight. It was a gradual process of observation, calculation, and debate, with each new generation of astronomers building upon the work of their predecessors. The path to scientific discovery is rarely a straight line. It's more like a winding road full of detours and unexpected turns. The geocentric model wasn't just a matter of appearances. It was deeply intertwined with philosophical and religious beliefs of the time. The Earth, considered the center of creation, held a privileged place in the cosmos. The heavens, with their seemingly perfect and unchanging celestial spheres, represented a realm of divine order. One of the most influential proponents of geocentrism was the Greek philosopher Aristotle. In the 4th century BC, he developed a comprehensive model of the universe that placed Earth at the center, with the sun, moon, planets, and stars all revolving around it in perfect circles. Aristotle's model, elegant in its simplicity, became the cornerstone of astronomical thought for centuries to come. However, as astronomers made more precise observations, they began to notice discrepancies between the predictions of Aristotle's model and the actual movements of the planets. Some planets, like Mars, seem to move backward in their orbits for a period of time, a phenomenon known as retrograde motion. These observations posed a challenge to the geocentric view. In the 2nd century AD, a Greek astronomer named Ptolemy devised an ingenious, albeit complicated, solution to account for the troublesome retrograde motion of planets. He proposed that planets moved not only in large circles around Earth, but also in smaller circles called epicycles. Imagine a planet tracing a loop-the-loop as it orbits Earth. Ptolemy's model, though complex, was remarkably successful in predicting the positions of planets with reasonable accuracy. It became the standard model of the universe for the next 1400 years, incorporated into the scientific and religious doctrines of both the Islamic and Christian worlds. While Ptolemy's model kept Earth at the center, it hinted at the underlying complexity of the cosmos. It showed that the universe wasn't as simple as it appeared. Sometimes the most elegant explanations aren't always the correct ones. Section 5. Copernicus arrives, shifting the center. In the 16th century, a Polish astronomer named Nicolaus Copernicus ignited a scientific revolution that would forever change our understanding of the cosmos. Copernicus, drawing on his own observations and the work of earlier astronomers, proposed a radical idea. What if the sun, not Earth, was the center of the solar system? In his groundbreaking book, De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres, published in 1543, Copernicus laid out his heliocentric model. He argued that Earth, along with the other planets, revolved around the sun. This simple yet profound shift in perspective had far-reaching implications. Copernicus's heliocentric model wasn't immediately accepted. It challenged centuries of established thought and contradicted religious doctrines that placed Earth at the center of creation. Yet the seeds of a scientific revolution had been sown. Section 6. Kepler, Galileo, and Newton, building a more accurate cosmos. Copernicus's heliocentric model wasn't perfect. It relied on planets moving in perfect circles. Johannes Kepler refined this model. He discovered planets move in ellipses. Galileo's telescope observations supported this. Isaac Newton explained why with his law of gravitation. Newton's law explained planetary orbits. Their work solidified the heliocentric model. Section 7. The dance partners, gravity's influence. Newton's law of universal gravitation revealed a fundamental truth about the universe. Everything is connected through the invisible force of gravity. Every object, from the largest star to the smallest grain of sand, exerts a gravitational pull on every other object. It's a cosmic dance, with gravity as the choreographer. In our solar system, the Sun, by far the most massive object, exerts the strongest gravitational pull. It's this pull that keeps the planets in their orbits, like dancers whirling around a central point. But the planets, despite their smaller size, also exert their own gravitational influence on the Sun. Imagine a large adult swinging a small child around in a circle. The adult, being much heavier, doesn't move much, but the child, lighter and more easily influenced by the adult's movements, swings widely. Now, imagine that the child also pulls back on the adult ever so slightly. This is similar to what happens in our solar system. Section 8. The Barycenter, a moving target. This brings us to the concept of the barycenter. The barycenter is the center of mass of two or more objects orbiting each other. It's the point around which these objects actually orbit. In a system with two objects of equal mass, the barycenter would be located exactly halfway between them. But in a system like our solar system, where the Sun's mass dwarfs that of all the planets combined, the barycenter is located much closer to the Sun. However, here's the catch. The barycenter isn't a fixed point. It's constantly shifting depending on the positions of the planets as they orbit the Sun. Sometimes the barycenter lies within the Sun itself, but at other times it can be located outside the Sun's surface. This means that the Sun isn't stationary. It wobbles slightly due to the gravitational tugs of the planets, especially Jupiter, the most massive planet in our solar system. Section 9. Why does the barycenter matter? You might be wondering, why does the barycenter matter? It seems like a minor detail, a cosmic technicality. But understanding the barycenter has important implications for astronomy. For one thing, it helps us to more accurately model the movements of objects in our solar system. When we send probes to other planets, for example, we need to take into account the motion of the barycenter to ensure that our probes reach their destinations. But perhaps more importantly, the barycenter concept highlights a fundamental truth about the universe. Nothing is truly stationary. Everything is in motion. Everything is interconnected through the invisible force of gravity. It's a reminder that our perspective matters. What we observe depends on our frame of reference. The barycenter also plays a crucial role in the discovery and characterization of exoplanets, planets that orbit stars other than our Sun. By observing the wobble of a star caused by the gravitational tug of an unseen planet, astronomers can infer the presence of that planet and even estimate its mass and orbital period. Section 10. Science, a journey of discovery. The story of how we came to understand the true nature of the solar system is a testament to the power of the scientific method. It's a story of observation, experimentation, and the constant refinement of our understanding. From the ancient Greeks who first gazed at the stars to the modern astronomers who use sophisticated telescopes to probe the depths of the cosmos, our quest to comprehend the universe has been a journey of discovery, full of surprises and paradigm shifts. The shift from a geocentric to a heliocentric view of the solar system, and then to the realization that even the Sun isn't perfectly stationary, illustrates that science isn't about being right or wrong. It's about constantly questioning, testing, and refining our understanding of the natural world. It's about embracing the unknown and being open to new ideas, even if they challenge our deeply held beliefs. Section 11, beyond the barycenter, what's next? So, the Sun isn't the center of the solar system in the strictest sense, but it's the anchor, the gravitational heart that holds our cosmic family together. And while the barycenter may seem like a minor detail, it's a reminder that the universe is a dynamic, ever-changing place full of wonder and mystery. As we continue to explore the cosmos, we're bound to make even more surprising discoveries that will challenge our current understanding and push the boundaries of our knowledge. The barycenter is just one example of how our understanding of the universe is constantly evolving. Who knows what other cosmic wonders await us out there in the vast expanse of space and time? The journey of scientific discovery is far from over. It's just beginning.
So hit that subscribe button, ring the bell for notifications, and let's turn the page on a new adventure together. Get ready to experience books like never before, only on VBook 360. Like, comment, and share to support the channel and keep the video magic alive. Thank you for stopping by. And remember, every video has a story, and every story deserves to be shared. See you in the next video.